Good afternoon, everyone. Welcome back to the Australian Institute of Physics Theoretical Physics Seminar Series for 2022. I'm David Tilbrook from the Department of Fundamental and Theoretical Physics at ANU, and I'm hosting this series of seminars on behalf of the AIP Theoretical Physics Group. I'd like to start, as always, by acknowledging the people of the Ngunnawal Nation, the traditional custodians of the lands upon which ANU and indeed all of Canberra is located, and we of course acknowledge the traditional custodians of lands all around Australia. We'd like to pay our respects to their elders, past, present and emerging. So far in this series of talks, we have had a wide range of fascinating seminars in topics of theoretical physics in such diverse areas as the philosophical interpretations of quantum mechanics. That was presented by Professor Howard Weissman. We've had a talk on neutrino physics by Professor Subhabhati Goswami, on the realization of discrete time crystals by Professor Stefan Rochelle, and most recently on the latest developments in the solutions and properties of the classical equations of fluid flow, particularly dealing with turbulence. That was presented by Professor Nigel Goldenfeld. All of these seminars and last year's seminars indeed are available to watch if you missed them on the AIP YouTube channel. They're easy to navigate to. Just go to your AIP YouTube channel and you'll see a link to them there. Or just go to YouTube and do a search on Australian Institute of Physics. Today's talk is entitled Searching for Dark Matter Scattering on Earth and in the Stars, and is presented by Professor Nicole Bell from the University of Melbourne. It's a great pleasure, in fact, to have an opportunity to introduce Professor Bell, who has made many contributions to Australian physics and Australian theoretical physics, and is the current Vice President of the Australian Institute of Physics. She is a Chief Investigator for the ARC Centre of Excellence for Dark Matter Particle Physics and leads the Centre's theory program. She has published many influential papers on dark matter and related subjects, and is the recipient of a number of physics prizes and awards in recognition of the work that she's done. These include the Bragg Gold Medal in 2001, the Chancellor's Prize for the University of Melbourne in 2002, the Sherman Fairchild Postdoctoral Fellowship at Caltech in 2004, and the Alvin Tolstrup Award at Fermilab in 2004, and most recently is the recipient of the Nancy Millis Medal in 2020 from the Australian Academy of Science, which people are aware of is a very prestigious recognition. As we are all aware, the search for the understanding about nature and properties of cosmological dark matter is one of the preeminent goals of modern physics and modern astrophysics, having potentially very profound effects on our understanding of the structure of the universe and the structure of matter itself. So once again, Professor Bell's talk today is entitled Searching for Dark Matter Scattering on Earth and in the Stars. Over to you, please, Nicole.
Thank you, David. Okay, so I'm going to talk about dark matter scattering, both in direct detection experiments on Earth and alternative ways of using astrophysics to probe the same interaction cross-section for dark matter particles. I should say that this work has been done in collaboration with a large number of people, but I particularly wanted to highlight the contribution of Giorgio, Jaden and Sandra, who are all past or present postdocs here at the University of Melbourne, who've played a key role in some of this research. Okay, so this is just a quick outline of what I'm going to talk about. I'm going to start with a general introduction to dark matter, then talk about direct detection experiments, and then astrophysical alternatives to direct detection experiments. All right, so by way of introduction, we have astrophysical observations which consistently point to the need for dark matter. And we see this at various different length scales in the universe, whether we look at galactic scales, where we see that in order to account for galactic rotation velocities, the galaxy has to be heavier than can be accounted for via the matter that we can see. Whether we look on the scales of clusters of galaxies, this is the so-called famous bullet cluster, where, among other things, we learned that the visible matter doesn't provide the bulk of the gravity. And on the larger scales associated with the whole universe, whether we look at the cosmic microwave background or the development of large-scale structure, we infer the need for dark matter and how much we need, and that the properties of that dark matter are the same on all of these scales. So we put together a consistent picture. I should say that all of these pieces of evidence for dark matter are sensitive to dark matter's gravitational influence. We know it's there because of its gravity. As yet, we have very little information about the particle properties of the particles that make up this dark matter. And as a particle physicist, it's those particle properties. What is the dark matter particle? How does it interact? That I want to learn about. All right, so how much dark matter is there? There's about 5 times by the amount of dark matter as there is ordinary matter. The rest is dark energy. But the fact that these numbers are kind of similar, a ratio of 1 to 5, similar orders of magnitude, suggests that actually the dark sector and the visible sector were once coupled. If there was absolutely no connection at all between regular matter and dark matter, you might imagine that there's no reason for these numbers to be anywhere near each other. They could be many, many orders of magnitude apart. The fact that these numbers are close is a hint, perhaps, that there's some coupling between the dark sector and the visible sector. And that's what we want in order for dark matter to be detectable. The idea of a WIMP takes that concept one step further. So a WIMP stands for a weakly interacting massive particle. And WIMPs are particles that have sort of coupling strengths and masses comparable to those that we see in the weak interactions. And the significance of that is that you naturally get the right amount of dark matter in the universe for those sorts of parameters. So there's something called the WIMP miracle. And so the basic concept here is that dark matter particles and regular matter were once in thermal contact. And in fact, there were rapid processes that interchanged the two. But at some point, the processes in which dark matter converts into regular matter froze out. So early in the history of the universe, when the temperature drops below a certain point, the cross-section for this process, the rate for this process can drop below the expansion rate of the universe. At that point, this process essentially stops, and the number of dark matter particles you have at that point is frozen in and doesn't change after that, except for redshift. So then if you know how much dark matter you need in the universe today, that tells you how big the size of the interaction cross-section ought to be. Actually, the density goes inversely, like the size of the cross-section. And you get the right numbers by throwing in a weak scale mass, or sort of a GeV scale mass, and a sort of a weak scale coupling. So a coupling comparable to the electromagnetic coupling. So this is the thing that's known as the WIMP miracle. And really, it's one of the most theoretically well-motivated ideas about where to look for dark matter, and it is in fact where most of the experiments are looking. So how would you go about detecting these WIMPs? You can try and make them in colliders. So this diagram shows the interaction of 2 standard model quarks to produce dark matter particles in the final state. You could try and make them in a collider, and in colliders you do searches for basically for missing energy. You can try and go in the opposite direction and look for the annihilation of dark matter particles back to standard model particles. And that's the sort of thing you would do with indirect detection, where you would look for the annihilation of dark matter, say, at the center of the galaxy, to fluxes of particles that you could see, be they gamma rays or neutrinos or antimatter. But the thing that I'm going to focus on most in this talk is the arrow going up the page, where I'm scattering a dark matter particle from a standard model particle to the same fun state. And sort of that elastic scattering process is what one searches for in direct detection experiments. Okay, so here's a typical direct detection experiment. So this is actually, this is how the xenon type direct detection experiments work, and I'll come back to this later. But for our purposes here, the point is that we have some incoming particles that come in, they scatter elastically off nuclei in the detector. You detect the very, very small nuclear recoil. And so the aim of the game for these experiments is to have a big enough target mass that the event rate is big enough that you can hope to detect it, and a low enough background rate that you can see the dark matter signal above background. And this plot on the right shows the evolution in time with some of these experiments. So the background rate is on the vertical, and over time we've headed in this direction. The backgrounds have been beaten down lower and lower, and also these experiments have been growing bigger and bigger because more target mass gives you more sensitivity. So where the field is at now is these experiments here, these little squares in blue, and where we're going in the future is towards this ultimate limit over here. And you see this magenta line across the bottom. This is the point at which the background that is most problematic for you with the detector is actually coming from the scattering of neutrinos from the sun or the atmosphere, are scattering in your detector and mimicking the dark matter signal that you're looking for. All right, so these plots show the current limits, or pretty close to the current limits, on the size of the dark matter scattering cross-section with nuclei as a function of the dark matter mass. And there are two plots because the answer is different depending upon whether the dark matter interacts with nuclei in a way that's independent of spin or whether it's dependent upon spin. In the case where it's spin independent, this is the most optimal case for detection, because what happens is that the dark matter particles can scatter coherently off all the nucleons in the nucleus. And so you get a big coherent enhancement because of that, and it allows you to probe smaller cross sections. So the current limits are seen down at about 10 to the minus 46 centimeters squared or so. In the case where the interaction is spin dependent, you essentially couple to the spin of the nucleus, and typically to one unpaired spin. And so you don't get this coherent enhancement, and the orders are a few, or maybe 5 orders of magnitude weaker. In both cases, you see this shaded region at the bottom of the plots. This is the level at which scattering of neutrinos, either from the atmosphere in this region over here, or from the sun, starts to look like the dark matter signal that you're looking for. And so this shaded region is called the neutrino floor. Once you hit the neutrino floor, you have this sort of irreducible background to start worrying about. And the next generation experiments are going to hit the neutrino floor. So these dashed red curves show you the cross-section sensitivity that we're expecting to reach with the next generation experiments that are being proposed at the moment. And at that point, you really have to start worrying about this neutrino background, how well it is that we know what it is, and how you would get around this background and still be able to detect dark matter. So in terms of challenges for the field, certainly the neutrino floor is one of those challenges. The next generation experiments will hit the neutrino floor. How would you get around that? One mechanism for getting around that is to try and do directional detection. So at the moment, you have the interaction is just dark matter particle comes in, scatters elastically off a nuclei. You see the nuclear recoil, energy deposited, but you have no directional information. If, in addition to seeing the nuclear recoil, you had some directional information that would allow you to reconstruct the arrival direction of the dark matter particle, then you'd be able to tell the difference, say, between a neutrino coming from the sun and a dark matter particle coming from the direction of the dark matter wind, which actually comes primarily aligned with the direction of the Cygnus constellation on the sky. And so there's a lot of R&D work going on at the moment about developing directional capability eventually for direct detection. And there's an Australian involvement in this so-called Cygnus experiment, which is one of the key players in this area. Okay, and one of the other key challenges for direct detection experiments in the future is probing the low mass region of parameter space. So you'll see in these sorts of plots I've been showing, the limits sort of get weaker when you get to dark matter masses of order a GeV or so. And the reason is simply that the nuclear recoils are below threshold. As you make the mass of the dark matter particle lower and lower, when it hits an atomic nucleus, it's a very light thing hitting a very heavy thing, and the momentum transfer is sufficiently small that the nuclear recoil is below the experimental thresholds. The nuclear recoil happens, you just don't see it. And so we want to know, how do we probe this low dark matter region of perimeter space? Okay, and there are a couple of, well, ultimately, to probe the low dark matter region of perimeter space, we're going to want new detection technologies with lower thresholds. But in the meantime, we can actually do some different analyses to probe this mass region using existing detectors. And the Migdal effect, which I'm going to spend a little bit of time talking about, is one of those strategies. All right, so yeah, I'm going to talk about the Migdal effect. And I'm also going to talk about ways to probe that region of perimeter space, not in scattering on Earth in our detectors at all, but in scattering in astrophysical settings. Okay, so let me start with the Migdal effect. So usually when we do direct detection, it's a dark matter particle that hits a nucleus and gives it a recoil. And most of the time, that's the only thing that will happen. But sometimes you can actually ionize that atom. So what happens is the dark matter hits the nucleus. From the point of view of one of the electrons in this atom, the electron sees a perturbed Coulomb field, and that can be enough to eject the electron from the atom. So basically, you have a nuclear recoil, and in addition to the nuclear recoil, you shake off an electron. And the probability for doing this is low, but this is particularly useful where you don't see the nuclear recoil itself because it's below experimental thresholds, but you do see that electron because that electron is much more detectable. And so we may miss the nuclear recoil, it's too low in energy, but we can instead detect this ionization signal. In terms of the kinematics, if you look at the nuclear recoil, the maximum nuclear recoil you can get is given by this expression here. This mu is the reduced mass. So for a very light dark matter particle, that reduced mass is the mass of the light dark matter particle, and then you're suppressed by a light mass divided by a heavy target mass, which keeps your recoil energy low. On the other hand, for the maximum energy of this Migdal electron, you don't have that suppression by mu on MT, and so you get much bigger. You can achieve much bigger energies in principle. So the Migdal effect is like a subdominant correction, if you like. Most of the time you just get a nuclear recoil. Sometimes you'll shake off the electron. It's a subdominant rate, but it's something that's much more detectable. You can ask if there are other subdominant processes that are much more detectable. And one thing you might imagine is radiating a photon from either the initial or final state nucleon. Again, that gives you something that's much more detectable with kinematics that are very much like the Migdal, but it turns out the rates are pretty low, that the Migdal wins by quite a bit. Okay, so coming back to the Migdal effect, this shows you the rates. The black is the nuclear recoil rate, and if you're above the threshold to see the nuclear recoil, this dominates by orders of magnitude. And then the colored curves are the rates for ejecting Migdal electrons. And there's these different colors for these different curves corresponding to where you eject that electron from, which orbital. Okay, so you see that the nuclear recoil, there is some threshold here above which the rates plummet. And so if your detector could detect large energies, but your thresholds are such that you don't see the stuff in black, your detection threshold could be out here where the colored region is. And in that case, you're going to be seeing the low rate, but observable rate of Migdal electrons, but you'll never see these low energy nuclear recoils. So that's really the region where it's most useful. And it can be used to extend the limits from experiments like xenon in time down into the low region of mass parameter space. So on the right-hand plot, the green and the red curves are the standard nuclear recoil limits, where you're just looking for that elastic scattering that gives you some recoil energy. And so that the red and the green are the regular analyses. And then the blue is the Migdal analysis, where you're looking for the Migdal electron rather than the nuclear recoil, which allows you to extend the analysis down a couple orders of magnitude lower in dark matter mass, where the nuclear recoil is below threshold, but you see that ionized electron. All right, so in terms of, so I should say that this effect has never been observed in this context. And so we can calculate the rates theoretically, but it would be really nice to have an experimental measurement that validated our theoretical calculations. And so if I look at the rate for these Migdal effects, this is the differential rate, and it goes like the standard elastic dark matter nucleus recoil rate times some ionization probability. And you can calculate these things, and there are some error bars on how well we can calculate this ionization rate. We can try and do the theoretical calculation better, but a calibration experiment would be really nice. There's an experiment at the moment actually called the Migdal experiment, which aims to do this with a relatively high energy neutron source, sort of MEV energy neutrons. But it would be really nice to have a calibration that achieved lower energies that more closely mimic the kinematics you would be interested in for the dark matter application. So we looked at the feasibility of doing this with a low energy neutron source, or actually low energy neutron sources and neutrino sources. So imagine you have some sort of neutron source impacting on some sort of xenon-based detector. Sort of to set the scale, this is sort of the relative event rate as a function of the energy of those neutron sources. So here, instead of firing dark matter particles at the detector, we're firing neutrons, but it's the same thing. We want to see the Migdal electrons rather than the elastic nuclear scattering. So here you see the elastic rate in black, the Migdal rate in blue. As I said, the Migdal rate is really subdominant, but this is useful when you're below threshold for those elastic scatters. So you see the elastic rate turn over here in terms of events if I put some energy threshold on those events. What sort of energies would be optimal for this? You want to be away from this low energy mess where there's a lot of resonances. So that argues for choosing a neutron energy above 10 keV or so. And you also, neutron energy below about 30 keV is optimal for keeping the majority of the elastic scatters below experimental thresholds. I mean, you want it to try not to be dominated by the elastic scatters more than you have to be. So we looked at this in the context of a xenon type experiment. So this is a little mock-up of something like the xenon N-ton experiment. And so what these are liquid xenon based experiments. What happens is the dark matter particle, or in our case, the neutron, comes in, has an elastic scattering interaction. You get a nuclear recoil, and some of the time you'll get one of these shaken off electrons. What do you detect? You detect scintillation light, which is a signal we call S1, at the point of that interaction. And then you get some ionization that drifts upward in an electric field. So there's an electric field between this cathode and anode, and that ionization, those electrons drift up, and then you get a second signal, a second signal that we call S2 in this gaseous phase at the top. And actually using the S1 and the S2 signals can tell you something about whether the event you're seeing was just a nuclear recoil or if it was an electron recoil. So we looked at the viability of using various different sources for neutron Migdal calibration experiment. And in the end, we focused on 17 keV neutron source, but we also looked at various different neutrino sources. And the rates of Migdal events are low as a fraction of the total number of elastic scatters. Actually, the SNS neutrinos actually give you the best in terms of the calculated ratio. But in fact, in terms of telling, distinguishing Migdal events, we eventually found that the neutron source is probably optimal. So these show you the signal in this S1, S2 plane. So remember, S1 was the first signal here, and S2 was the ionization signal in the gaseous phase. And in the cases where you have an electron recoil or you eject a Migdal electron, you get more electrons and therefore more of the S2 signal than you would get if you strictly had a nuclear recoil. And so this is what we see here, that the nuclear recoils are clustered down here. This is for the neutron source, and the Migdal signals are clustered up here, as you might expect. For a high energy neutrino source, actually the separation between the nuclear recoils and the Migdal events was much less clear. So it was this neutron source that was optimal. So we concluded that it would be feasible to do a calibration experiment using relatively low energy neutrons. All right, I want to switch gears and talk about inelastic dark matter. And in fact, the Migdal effect is also a type of inelasticity in nuclear scattering. So standard direct detection searches look for dark matter nucleon elastic scattering. The Migdal effect, if you like, is a type of inelastic scattering, but there are other ways in which dark matter nucleon scattering can be inelastic. And one of the ways that theorists like to talk about often is a sort of inelastic scattering where you're exciting the dark matter from one mass state to another. So in this scenario, we don't have a single dark matter state, but in fact two, which are two almost degenerate dark matter states separated by some small mass splitting delta M. And this may seem like an unnecessary complication, but in fact, this is quite a natural scenario that arises in a bunch of models. And if this is what nature looks like, then direct detection experiments are, what you see in a direct detection experiment is quite changed. In these models, they're called inelastic because the scattering of the light state to the light state is actually absent from the tree level Lagrangian altogether, or it's highly suppressed. And in these models, the dominant process there, therefore, is the scattering from one mass state to the other. But the trouble here, though, is that we're talking about highly non-relativistic dark matter, and we need to have enough kinetic energy to go from the lighter state to the heavier state. And that means this is not going to go kinematically unless that mass splitting is small enough that you can access that higher state. So this is kinematically inaccessible unless the mass splitting is pretty small. For direct detection experiments, that limits you to KeV scale mass differences. Bigger mass differences can be accessed if you can boost the dark matter to relativistic energies. I think I'm going to run out of room to talk about these, but you can boost it in a variety of ways. Scattering in neutron stars that I'll come back to, and boosting by scattering with cosmic rays and a variety of other mechanisms. But I wanted to talk about one particular paper in which we looked at a type of inelastic dark matter. And this was motivated by an excess seen by the Xenon 1 ton experiment, sort of mid-2020. And so this was the key plot from the Xenon 1 ton collaboration. So this was their event rate as a function of recoil energy, and what they expected to see was something like the red line, and what they actually saw, well, you can see the data points, they had an excess of events at around 2 or 3 keV. And the explanations for such an excess of these scattering events at that energy in the paper from the collaboration was that maybe there's some unaccounted for tritium beta decay background, maybe it's solar axions. A large neutrino magnetic moment, interestingly, can do this. In fact, the dark matter experiments, direct detection experiments, are now starting to become really competitive for setting limits on fundamental neutrino properties, which is an interesting development. So in any case, this excess caused a flurry of activity in the theory community, who put out proposed explanations for this effect. And so I'm just going to talk about ours. We proposed that this was due to the scattering of inelastic dark matter with a small mass splitting, a mass splitting of about 3 keV. So what happens is that dark matter particles scatter with nuclei, either in the detector itself or nearby, excite the dark matter into the heavier of these states that has this, they have this 3 keV mass splitting. The heavier one decays back to the lighter one and releases a 3 keV photon. And then we would say that, okay, what's being seen here is actually a photon line, is accounting for those events. When you do a fit to that, you see that the photon line actually fits the data quite well. And so, yeah, in fact, it's a pretty good fit to the data. Oops. And this is a testable scenario because in addition to that photon, you should also be able to see the nuclear recoil. And that is such that, in fact, there's only a narrow range of masses for which this would work at the moment, below about 15 GeV. But as the xenon experiment takes more and more data, they'll be able to either exclude this regional parameter space or confirm it. So that's an interesting thing to watch how the next data release from xenon looks like. Okay, I am going to run out of time, so I'm going to switch to dark matter capture in stars. Okay, so you should think about dark matter capture in stars as an alternative to direct detection, something that's complementary to dark matter direct detection experiments. And so this picture is sort of a cartoon of the basic scenario. So imagine this is the sun, but we can equally well replace it with some other object, a white dwarf, a neutron star, Jupiter, the moon, doesn't matter. So this is a dark matter particle from our halo, which scatters in the sun. So remember, the interaction that we're looking for on Earth are dark matter particles scattering with nuclei. So if they can scatter with nuclei in our detectors on Earth, they can scatter with nuclei in the sun. If a dark matter particle had a scattering interaction with a nucleus in the sun, typically what happens is that the dark matter particle loses enough kinetic energy to fall below the escape velocity for the sun, and then it's gravitationally bound. Not necessarily within the sun, it will sort of go be orbiting around, but over time and subsequent interactions of this gravitationally bound dark matter will lead to these particles losing all of their kinetic energy and thermalizing within the sun and settling down in the core of the sun, where a increasingly big concentration of dark matter is built up. Once that dark matter is in the center of the sun, there is some probability that it will annihilate. Remember that we know something about the annihilation cross-section for dark matter particles, because that's what sets the relic abundance in the universe today. So the dark matter particles are captured, they build up in the center of the sun, they can annihilate in the center of the sun, and then you can look for signals of dark matter annihilation in the center of the sun. All right, so what would you see? Almost any standard model particles that the neutrinos that the dark matter can annihilate into would be trapped in the sun. You make photons, electrons, quarks, whatever, they're going to be trapped. The only exception to that statement is neutrinos. And so you might imagine that you get high energy neutrinos coming from the annihilation of heavy dark matter in the center of the sun. And indeed, the big neutrino experiments, Super K, Ice Cube, and so forth, have for decades been doing these analyses where they look for not only solar neutrinos that we expect, but also high energy neutrinos coming from the center of the sun. This is really very, very complementary with direct detection, because typically, actually maybe the next slide is better. Okay, so this is the evolution of the number density of dark matter particles in the sun. It grows as you capture dark matter particles. It decreases as you annihilate them away. For very low masses, you worry about evaporation. This is where you have scattering interactions which bump the dark matter energy up above the escape velocity again. This turns out to be negligible unless the dark matter is pretty light. So for simplicity, let me ignore this term. And then if I focus on the first two, and you can solve this, it's really simple. And you find that the number of dark matter particles as a function of time goes like this. And for sufficiently big times, this just asymptotes to square root C on A. And in that limit, the number of dark matter particles in the sun is constant because the rate at which you're capturing them and the rate at which you're annihilating them away balance out. And for the typical sorts of parameters that we're interested in, sort of annihilation cross sections that are the right size to give you the relic density of dark matter in the universe today, and capture cross sections anywhere near the vicinity of what we can probe in direct detection experiments, you indeed reach that capture annihilation equilibrium. And what's nice about that equilibrium is that the signal is constant as a function of time, but moreover, the size of the signal that you might detect in IceCube or Super K is controlled entirely by the rate at which you capture the dark matter. And the parameter of interest for that is the dark matter nucleon scattering cross section, precisely the same parameter that we're trying to measure in direct detection experiments. So you can put the results on the same plot as the direct detection experiment results. And so let's see. So this is the spin dependent dark matter. The shaded yellow are currently the best limits on dark matter spin dependent scattering with nuclei. So this is the cross section as a function of dark matter mass. The shaded yellow is ruled out by the PICO experiment. And then some of these colored curves down the bottom are the limits that you get from not having seen high energy neutrinos come from the center of the sun. So these lines out at large dark matter mass come from IceCube. These shaded bands are our calculation for what can be done in Hyper-K, which is the forthcoming successor to the Super Kamiokande experiment in Japan. And so you see that there's currently some region of parameter space where you can do better looking for neutrinos coming from the sun than you can do by looking in a conventional direct detection experiment on Earth. I should say it's worth playing this game only with spin-dependent interactions, because the spin-independent ones, for which the direct detection experiments have that coherent enhancement, that they win. That those direct detection experiments with the coherent enhancement in play are now so sensitive that they always win. So I said that the only thing that could get out of the sun is neutrinos, but that assumes that the dark matter annihilates into standard model particles. And in fact, that may be too simplistic. In many dark matter models, the dark sector consists not only of the dark matter particle itself, but new particles which mediate the interactions between the dark sector and the visible sector. And so it's very popular model has something called a dark photon in it, which is like a regular photon. In the dark sector, it can mix with the standard model photon via kinetic mixing. But there are also versions of this model that involve scalars instead of photons. It's very easy to write down a simple, elegant model in which there's some new light mediator which couples the dark sector to the visible sector. And then you have a scenario in which the dark matter can annihilate not only to standard model particles like neutrinos and other things that get trapped, but also to dark sector particles, these dark photons or other dark sector particles. And because they live in the dark sector, they wouldn't be trapped. They would actually get out of the sun. Of course, anything else that lives in the dark sector has to eventually decay back to regular visible standard model particles. Otherwise, it would be the dark matter itself. And so dark photons are expected to decay to electrons and positrons. Dark scalars are expected to decay to photons. And so now you have a scenario in which You can look for other signals coming from the center of the sun, high energy gamma rays coming from the center of the sun, electrons and positrons coming from the center of the sun. So we looked at high energy gamma rays. There are recent measurements of the gamma ray flux from the sun, actually upper limits in the very high energy range. Let me skip this. And it turns out that you get interesting limits on the size of the dark matter scattering cross-section, not only for the spin-dependent case, but even for the spin-independent case, which I said was hopeless for the neutrino observations because direct detection experiments are so strong. Well, in these dark photon models where you have dark photons getting out of the sun and then decaying back into something that you can see, you can even explore regions of the parameter space well below direct detection experiments. Okay, but finally, neutron stars. So the sun is good at capturing dark matter, but neutron stars are better. And they're better just because of their extreme density. Neutron stars capture dark matter very efficiently. And if you plug in the numbers, the numbers are kind of interesting. The figure of merit, if you like, for the capture of dark matter in an object like a star is the cross-section for which the capture probability becomes order 1. So that's the limit where if I have a dark matter particle that traverses the star, it has an order 1 probability of scattering. And if you plug the numbers in for a neutron star, so this is sort of the geometric limit, you get a cross-section of 10 to the minus 45 centimeters squared. And what's interesting about this number is that this is approximately the cross-section limits from the current best direct detection experiments in the region where they're most sensitive. So the masses are comparable to the mass of a nucleus. The scattering is spin independent, so it's coherently enhanced. And the cross sections are not suppressed by velocity or momentum suppressions. So neutron star sensitivity is comparable to direct detection experiment when everything is going right for direct detection. And actually the sensitivity is much, much more sensitive than direct detection experiments in the cases where everything is not optimal for direct detection. So if neutron stars can capture dark matter so efficiently, you can ask crazy questions like, can they capture so much dark matter you could collapse a neutron star to a black hole? This is possible, but not very probable for the typical type of WIB dark matter that we spend most of our time thinking about. So it is possible, but you need certain things to all fall in line. You'd want to capture the dark matter, but not annihilate it away. You don't want it to be fermionic with some, and you certainly don't want it to have attractive self-interactions. If you're trying to make neutron stars collapse through some accumulation of dark matter, it helps you if the dark matter is a boson. You want to turn off any sort of repulsive self-interactions that might support you against collapse. You can arrange for black holes to be formed, but it's certainly not going to happen for a typical WIMP. But there's been a lot of interest in dark matter accumulation in neutron stars in the last couple of years. And this is essentially because it's been recognized that they can heat the neutron star up. So what happens when you capture the dark matter particle is that you're transferring kinetic energy from the dark matter to the neutron star. And that kinetic energy can actually heat the neutron star by about 2000 Kelvin. And then if the dark matter that you've captured also self-annihilates, you get some additional heating. But either way, we're talking about heating of order a couple thousand Kelvin. And if you can compare that with the temperatures to which neutron stars are predicted to cool, then in principle, you could see this. Neutron stars are supposed to cool to say 1000 Kelvin or so after about 10 megayear, and after longer times get really quite cold. So in principle, neutron stars get really quite cold. Whether you can see such a cold neutron star is an observational challenge, but in fact, the prospects seem to be reasonable. Okay, the coldest neutron star that's ever had its temperature measured is about 10 to the 4 Kelvin. We would like to see 10 to the 3 Kelvin. So an order of magnitude away, it's not crazy. And there are some papers looking at the observational prospects who conclude that this is actually quite feasible in the near-term future. So essentially, you need to find an old, cold, isolated neutron star that's not accreting stuff and getting heated up. And then you need to follow up and measure its temperature. And so for the temperatures that we're measuring, sorry, for the temperatures that we're talking about, this would be near infrared emission. But let me come back to why you might like to think about this. And that's because there's a whole bunch of interactions which actually we're never going to probe in direct detection experiments that maybe you could learn about by thinking about dark matter capture in neutron stars. And the difference is all about kinematics. When the dark matter infalls to the neutron star, it is accelerated to quasi-relativistic velocities, which make the kinematics completely different to the scattering of highly non-relativistic dark matter on Earth. So when we're looking for dark matter scattering in a direct detection experiment, we're hoping that the cross-section is not suppressed by some power of velocity or momentum, because if it is, that would kill off the signal. We're hoping that it's spin independent, so we get that coherent enhancement. But if the cross-section turned out to be, if the interaction type turned out to be one that gave you a velocity or momentum suppressed cross-section, detecting it in an experiment on Earth would be very, very hard. We would be orders of magnitude away from seeing that. But in fact, the neutron star doesn't care about that because the dark matter is quasi-relativistic. So there are some interactions that you'll never see in direct detection experiment that in principle you could learn about with astrophysics. So the capture of dark matter in stars in general and neutron stars in particular has been studied for about 30 years. But in fact, the neutron star calculation has been done not very well until quite recently. The calculations that were done for the sun were sort of applied to the neutron star without making all the necessary changes you need to make to account for the extreme environment of the neutron star. And so the work of my group, but particularly Giorgio, Sandra, and Michael, has been looking in particular at adding all the different physics that really ought to go into these neutron star calculations. So consistently dealing with the neutron star structure, making sure you're including gravitational focusing, making the calculations fully relativistic actually matters, particularly for scattering off the relativistic degenerate electron component of the star. Adding a bunch of other effects, Pauli blocking is really important. But there are a couple of effects that were completely absent from previous calculations that actually make a really big difference. And the first one is sort of just simple kinematics. Most of these calculations in the past were done where we take the cross sections and calculate them as we would calculate them for direct detection experiments where the momentum transfer is really small. But in fact, for scattering in neutron stars, the momentum transfer is pretty big. And so the hadronic matrix elements actually have a momentum dependence that's calculated in the zero momentum transfer limit for non-relativistic scattering. And that's an approximation that should not be made for relativistic calculations, and it leads to a suppression actually of the scattering rate. And another correction is that in fact the nucleons of the neutron star are not a free gas of particles, we're actually strongly interacting. And when we account for these effects, we actually change the answer for the scattering rate by up to 3 orders of magnitude, which is not a small correction. But let me jump to the punchline. These are the cross sections that one could probe. The dark matter nucleon scattering cross-section is a function of the dark matter mass. If one were to observe an old cold neutron star, that we could say, aha, that one hasn't been heated up. That one lives in a dark matter rich environment, but it hasn't been heated up by scattering. So I said that the ballpark number was 10 to the minus 45 centimeters squared, and that was just the geometric limit that gave you an order 1 probability of scattering when you went through the star. And so this flat region in these curves is about 10 to the minus 44-ish. You'll see that the sensitivity weakens both for low mass and high mass. And these are 2 different kinematic effects. In the low dark matter mass regime, what's happening is that there's Pauli blocking going on. So you need to scatter from one nucleon energy state to another. In order for that process to go, you need the momentum transfer such that it's bigger than the neutron Fermi momentum, or there's no empty state for the final state neutron to be in. So Pauli blocking restricts the scattering on these degenerate neutrons when the dark matter mass is low, because for those low masses, the momentum transfer is low. And then for high dark matter mass, you have a different problem. For a sufficiently large dark matter mass relative to the target mass, and the targets are, say, neutrons or protons, then the momentum transfer in a single collision is not sufficient to drop that dark matter particle down below the escape velocity for the neutron star. And in that case, you need multiple scattering interactions in order to transfer enough kinetic energy. So again, you get a suppression and the sensitivity gets worse for very large dark matter mass. But you'll see there's a range of dark matter masses that can be probed. I should say that the shaded pink is the current limits from direct detection experiments. So this plot is for the case where everything is optimal for direct detection. It's unsuppressed spin-independent scattering. The yellow is neutrino floor. But what's interesting is that you probe really large region of neutrino masses, well below the thresholds below which direct detection experiments currently can't see the nuclear recoils, up to very large neutrino masses. And if I show you the plot for, okay, so this is spin independent and this is spin dependent. If I show you the plot for spin dependent scattering, actually you do better than all the existing direct detection experiments at the moment, and the forthcoming ones, which is this dashed curve, and you even probe well into the neutrino floor, where dark matter direct detection is going to struggle to go without new approaches like directional detection. In both these cases, the interaction that's been assumed is unsuppressed by powers of velocity or momentum. If I were to throw in an interaction type that had a velocity or momentum suppression to its cross-section, then the shaded pink region from direct detection would disappear altogether. You can look at scattering not only from the nucleon component of the star, but also the lepton component. So neutron stars contain neutrons, protons, electrons, muons in beta equilibrium. They probably also contain exotic matter. But we have relatively good estimates of, for example, the electron number density is a function of radius, the chemical potential, which matters a lot. And so you can repeat these calculations for the scattering of dark matter particles from electrons and muons. And you can compare that with the best electron recoil measurements coming from direct detection experiments. So I've concentrated in this talk primarily on dark matter scattering with nucleons. In fact, it might be the case that dark matter doesn't interact with nucleons, but only interacts with leptons. And so in that case, you want to look for not dark matter nucleon scattering, but dark matter electron scattering in your detectors. And so this is the neutron star equivalent of that, the sensitivity that you would get by observing an old cold neutron star on the dark matter lepton scattering cross-section is given in blue and pink for electron and muon scattering, respectively. And again, you're probing orders of magnitude below where the best terrestrial electron recoil results sit at the moment. And you're probing potentially into below the neutrino floor and down to low dark matter masses, which are below experimental thresholds for picking up electron recoils. I'm probably running out of time, but let me spend 1 minute talking about white dwarfs. So everything I've said about neutron stars are potential limits because we haven't yet observed a sufficiently old cold neutron star. The observational prospects are reasonably good, but we haven't seen one yet. But you can think about these kinds of ideas and apply them to objects for which we have measured their temperature. And so they're a good white dwarf observational data. And so you might think about doing this with white dwarfs instead of neutron stars. Neutron stars are, the ultimate, the densest object that you want to consider. But white dwarfs have got more observational data, and we understand them better. They've got well-defined mass radii relations. There's less uncertainty about their equations of state. I didn't talk about the neutron star equation of state, but I sort of glossed over that for white dwarfs. There's much less uncertainty. They're better understood objects. So we looked at white dwarfs in the M4 globular cluster, and we assumed that that M4 cluster lives in a dark matter subhalo. That assumption isn't absolutely necessarily true. So this is the assumption that has a question mark about it. What do we know about the dark matter density of M4? But assuming it formed in a dark matter subhalo, because the jury is still out on that. But assuming it formed in a dark matter subhalo, we can do the same sort of thing that we did with the neutron star. This is a plot of the measured luminosity of some of the white dwarfs, and M4 as a function of the mass of the star. The particular ones that give you the best limit, you might think they're the low luminosity ones and the high mass ones. High mass because the heavier objects capture more efficiently, and low luminosity because we're trying to see the heating, so it's better if they're colder. And so it's these higher mass, lower luminosity stars that give you the best limits. And here's the equivalent plot that I showed you for neutron stars. The limits are weaker than neutron stars, but if you make reasonable assumptions about the dark matter density for M4, then these are existing limits rather than projected limits as they are for the neutron stars. Okay, so again, you potentially go into the low dark matter mass region of parameter space where it's really hard for direct detection to reach. And for the electron case, you're well below the best electron recoil limits and starting to get towards the neutrino floor region. Okay, so let me summarize. There's a lot of experimental activity going on in the dark matter community at the moment. And in fact, the dark matter community and the neutrino communities are starting to merge, not least because the dark matter experiments are heading towards the neutrino floor. And we're getting to the point where we'll be able to do neutrino physics with dark matter detectors and vice versa. But the key challenges for the experimentalists are that they're going to hit the neutrino floor, and the low mass dark matter region, where the nuclear recoils are really small, requires new experimental techniques. In terms of new approaches, we either need new types of detection technology, for example, to reach that low dark matter mass regime, or to develop directional capabilities so we can see beyond the neutrino floor. And in the meantime, we can do new analyses using existing detectors, such as using the Migdal effect. And then finally, I hope I convinced you that actually there's a lot to be gained by looking at complementary information that comes from astrophysics, and to use this information to better hone where you look in direct detection experiments on Earth. Because if you could observe an old cold neutron star, you would learn something really important about what sort of dark matter scattering cross sections are feasible, are plausible. Thank you, I'll stop there.
Thanks very much, Nicole. That was really, really interesting. We've only got one question queued up on the Q&A so far, then I might ask some naive questions. Christopher Graham wanted to know, could you get any recoils being caused by interactions with virtual particles? And if so, I guess, where would the limit of that be in relation to the sensitivity of the system that you've got?
In direct detection experiments?
Yes, I think that's what he was referring to.
So I'm not entirely sure what he means by virtual particles. I mean, the virtual particles mediate the scattering interactions anyway.
Yeah. Yeah. I mean, I think if it did, it would be down at the sort of extreme lower limits, I suspect, if any of that was happening. Peter Riggs asks, he says, what do you think of the possibility of so-called heavy neutrinos being detected in dark matter interactions?
I mean, so heavy neutrinos are a plausible dark matter candidate, right? Heavy right-handed neutrinos with the right sort of couplings could be WIMP type dark matter, or yeah, I mean, this is a viable dark matter candidate.
Right.
And we wouldn't, from the nuclear recoil experiments themselves, provided the couplings were the right size to see it at all, we wouldn't tell the difference.
Yeah. And I mean, and all of this work, of course, is assuming out of necessity that the dark matter are weakly interacting particles. I guess if they're not, we're back to square one, right?
Well, we're not back to square one. I mean, there are two types of dark matter, which is much more well motivated than anything else. One of those is WIMPs, and the other one are axions, for which you need a whole different set of experimental approaches to look at. There's a group in Perth who are doing some important work on that. And there's a big axion community worldwide as well. Those are the places where the experimental effort is focused, but they're focused there for good reason.
Right. I say, of course. Peter Price would like to know, does the distribution of dark matter in the universe, somewhat independent of visible mass, put bounds on the dark matter capture by stars, etc.?
Does the distribution of dark matter in the universe put bounds on the... Yeah, so the capture and star calculations assume something about the local density of dark matter.
Yeah, okay.
So if it's neutron stars in our galaxy, I mean, we've got a reasonably good idea about the halo density profile. The dark matter density is a function of radius in the galaxy. If it's somewhat, so we're certainly not assuming uniform dark matter density throughout the universe. We assume it's clustered into halos and so forth.
And to get a feeling for that density, does that come from gravitational lensing observations, or where do you get those numbers from?
So this is not my area of expertise, but yeah, we get those numbers from the astrophysicists. So there's the local dark matter density for capture in the vicinity of the sun is sort of well tied down. The one that's most uncertain in the work that I was talking about was the density in the M4 globule cluster, for which there are a couple of different schools of thought.
Okay, right. And then a simple naive question, having not read about anything about the experiments before, the experiment, the calibration experiment, if you like, that you described on slide 21, the detected particles are photons, right? And are they X-ray photons that you expect, or optical photons, or what sort of energy are we talking about?
Hang on, slide 21.
Yeah, that was your diagram of.
Oh, okay.
Yeah.
So the dark matter particle comes in and scatters, and so forget about the Migdal effect. Usually what you're getting in, you're getting a nuclear recoil, and that's depositing energy. You see scintillation light in the detector, exactly.
Right. Okay, right.
And you also get some ionization, and that is drifted upward in this electric field, and you get a second signal here. But so there's scintillation here, and then a second signal from the ionization that reaches the gas phase. But fundamentally, it's an elastic nuclear recoil.
Right, I see. Okay. And how close are these experiments to being able to be done, would you say?
This Migdal calibration experiment.
Yeah.
The challenge with that is that the Migdal rate is much smaller than the elastic nuclear scattering rate, so only a small fraction of the events. And in fact, the fraction is in this table for the assumptions in our calculation. Only a small fraction of the events have an ejected electron, which is the thing that you're trying to look for. And there are also backgrounds that are important. So if neutron capture and then subsequent de-excitation actually provide some of the backgrounds for these experiments, and you can see the neutron capture cross-section here in red, which is not insignificant. So we have some plausibility arguments about how you might reduce those backgrounds through various cuts and possibly pulsing of the beam. So there's some timing information.
Right.
But the backgrounds are, yeah, really important. It's all about thresholds and backgrounds.
Yeah, yeah. Peter Price had a follow-up question. Could you please repeat what you said about the effect of nucleon structure and dark matter scattering? I think you said there were 3 orders of magnitude change. And I also wanted to ask something about that. It's fascinating, the difference between the spin-dependent and spin non-dependent calculations that you've made. I was just wondering if you could say a little bit more why they're so different.
Okay, so first of all, I think the first part of the question was referring to this.
Yeah.
We're so used to doing dark matter nucleon scattering calculations in the zero momentum transfer limit, because for experiments on Earth, that's the only thing you ever think about.
Yeah.
And when you do scattering in the sun, which is what people have done for decades too, the velocity of dark matter particles when they hit the sun is a tiny bit bigger, but they're still highly non-relativistic. So those limits are all fine. But when the momentum transfer sort of becomes GeV scale, then the zero momentum transfer limit isn't good anymore. So there's some hadronic matrix elements that go into the dark matter nucleon scattering cross section that should be amended to put in their momentum dependence. And that's all we did there. So it's actually a really simple perturbation to, the standard calculation that everybody does, but it changes the answer by quite a lot.
Right, I see. Right. And then later on, for example, on slide 50, I think. No, slide 35, I think. 36, something like that. You showed the differences between the spin and non-spin dependent interactions. I think it was slide, I'm trying to remember what slide it was now.
Yeah, I think actually the one right at the start might be the best.
Yeah. Yes.
That might be the most illuminating.
Yeah, that's great. Yeah.
And I should probably have had a slide on why these are so different.
Yeah.
Really, for the plot on the right, you're interacting with a single nucleus in the nucleon. And on the one on the left, you're interacting with the whole nucleus coherently. So it's spin independent. And so there's the amplitude for scattering on each one of the nuclei in the nucleus are just added coherently. And so you get an enhancement that goes like A squared, where A is the atomic number of the relevant isotope. So you pick up, and A is of order 100, so you pick up maybe 4 orders of magnitude increase in the size of the cross section, and therefore decrease in the sensitivity, just because of that coherent enhancement that you get for the spin independent interactions that you don't get for the SD ones.
Oh, I see. Okay. Right. The sort of the Migdal effect that I'm familiar with in the past from solid state physics and a few things, I guess, is the Landau Migdal effect, which is really a quantum effect where the wavelength of particles is much longer than the typical scattering density, if you like. So it's a quantum mechanical effect to some extent. That's distinct from the simple Migdal effect that you're referring to here. Is that correct?
Yeah, that sounds like something different to me. Yeah.
Right, I see. Yeah. Okay. Well, that was, yeah, it's very, very interesting. I just look at my notes to see if I had any other questions I forgot to ask, or if there's anything else on the panel. No, I think we just about covered it. Thank you very much, Nicole. That was really, really interesting. So where do you reckon, do you have a feeling for what experiment you think is the most likely to first reveal some interesting properties in dark matter, or am I nailing you down a bit too too stringently?
That's really hard to say. I mean,
yeah.
There's like a 3-pronged approach to looking for these WIMPs, right? It's a combination of the collider searches, the indirect detection searches, the direct detection searches. The indirect detection ones, a bunch of signals have been claimed over the years that haven't stood the test of time.
Yeah.
And it would be nice to see signals in multiple challenges as a sanity check.
Yeah.
Indirect detection alone has the drawback that you can never be completely sure that it wasn't some garden variety astrophysics that you didn't understand properly.
Yeah.
Collider, you might produce dark matter particles. You might produce something that looks like a dark matter candidate, but to know that it's really the dark matter candidate and it's a particle which is stable on a time scale of order the age of the universe is something that you're not going to get from a collider experiment.
Yeah.
It's the direct detection experiment that's going to the one where you're going to be confident that it's dark matter that you've detected and not something else. So those experiments are really key, irrespective of what we find in colliders or in direct detection. It'd be nice to have detections in all three, but if we had a detection one, we'd want the direct detection as well. Which mass and cross section? That's really hard to say because theorists can invent a lot of models, right?
Yeah, yeah.
But the WIMP parameter space remains really well motivated.
Right. Okay. Okay. And then there was one last question from Igor. He wants to know, is xenon ideal for maximizing the Migdal process and phenomena that you're looking for?
Is xenon ideal? We also looked at argon, which is a typical detector element used in some of these experiments as well. There were pros and cons for the argon versus xenon. But in general, yeah, that those xenon experiments are sort of ideal. Yeah.
Right. Yeah. Right. Well, that was really interesting talk. Thank you very much, Nicole. I just remind everybody before we wrap up that you'll be able to watch this seminar again in a couple of days. It'll be on the AIP YouTube channel. I'll certainly be looking at it again to digest a bit more of the subject. And we will keep everyone informed as to when the next talk is coming up, which will be roughly in 3 weeks' time. Thank you very much, Nicole, and thank you everyone for attending. That was great.